Okay then, so let's proceed with the next example here on the voltage divider bias. So figure Q3 shows a circuit configuration with 1 voltmeter. So basically here we are putting a voltmeter between ground and the gate terminal, gate terminal of the MOSFET circuit configuration, and we get the 18 volts reading on the voltmeter. State the name of the circuit. So this is simply a voltage divider bias circuit. And how do we know? Based on the connection, the R1 connection between the source VDD, the voltage source VDD, and the gate terminal of the MOSFET. Sketch the transfer characteristics. So for the transfer characteristic, this is looking at the ID VGS, the ID VGS curve, where we need to get the load line, and also the exponential curve, the load line in the curve. So for that we need to calculate the V Thevenin if it's required, but in this case we can see that the voltage across R2 is 18 volts. So it's 18 volt there. So the voltage seen between the gate and the ground is 18 volts, which means that our V Thevenin is in fact 18 volts. But first we need to calculate our K here. So our K is ID on divided by VGS minus VGS TH, VGS on squared, and this one we should get, so if you do this calculation, is 3 milliamps divided by 10 minus 5 squared, and we should be able to get 0.2 so 0.12 milliamps per voltage squared. So that's our K value, and we get our first equation for the transfer characteristics, which is ID is equals to K VGS minus VGS TH squared. So this is 0.12 VGS minus 5. Our VGS TH is 5 squared. So from here we can derive our table, the ID VGS characteristics table, and we can draw the graph. We can draw the line in the graph. So this is number one, and number two. Number two is the loop here. The number two is the loop there. So the loop there, we are looking at 18 minus VGS. So VGS is here. 18 minus VGS plus minus. So 18 minus VGS minus IDRS is equals to 0. So VGS is simply going to be 18 minus IDRS. And RS is given as 0.82 kilo ohms. Done. And next we are going to look at this KVL loop, the drain source. So for the drain source KVL loop, what we're going to have is 20 minus IDRD minus VDS minus IDRS is equals to 0, and therefore your VDS is simply equals to 20 minus ID RD plus RS. So ID plus RD plus RS is 3.82, 3.82 kilo ohms, and here you can say that it's 20 minus ID, 3.82 kilo ohms. So to get our VDSQ. So this is number 2 and this is number 3. So we have all our three equations. Then we can calculate our operating point, and also we do the graph and we get the IDQ and VDSQ. So if you do the graph, you are going to get something like this. So we are going to get Okay, so in your case, you need to use a graph paper. Okay, if you don't have a graph paper, I think you should get a graph paper and draw carefully, neatly. Okay, I'm just showing as an example here. What we're going to get here is we're going to get 18. Okay, so we're going to get 18, maybe around 18 here. Okay, sorry, so 18 volts. Okay, based on this one. Okay, 18 volts, and then RS is 0.82, and here is actually 20. So I'm getting 22. Okay, here is 22, right? 22 milliamps, and this is ID. This is VGS. Okay, so 18 volts. Okay, and 18 divided by 0.82 is 22 milliamps, and you just make your load line like so. And then if you do this one, okay, if you do the table for this one, you are going to get starting from 5, so 9 is somewhere there, 5 is somewhere here. So it's starting from 5, and it's going to go up from 5, and it's going to intercept at around 12.6. Okay, so this is 9. Okay, so here is around 13. So 12, I'm getting around 12.6. So 12.6 is going to intercept there. So you're going to get something like this. Okay, 12.6 volts, and your ID is going to be around 6.5 milliamps. Okay, so 6.5 and 12.6 volts. And then if you substitute 6.5 there on the VDS, we are going to get the VDS-Q. So and for VDS-Q, I'm getting the value of okay, I think I've not calculated VDS-Q, but basically if you put 6.5 in this value ID here, you are going to get some value for VDS-Q. Okay. Okay, so done. Okay, so number 3 is tricky. Okay, number 3. So for number 3, what happened to the Q point if R2 is reduced by half? But getting back to number 2, in this case, we don't need to calculate our Thevenin. Okay, our Thevenin resistance and our Thevenin voltage, because we already know the voltage looking at the gate input. Okay, so the voltage looking at the gate input here, relative to ground, is given by the voltmeter. Therefore, that is actually your Thevenin voltage. Okay, so for number 3, okay, what happened to Q point if R2 is reduced by half? Okay, so let's okay, so we can just give a moment to okay. So what happened to the Q point if R2 is reduced by half? So we have R2 here. Now R2 is reduced by half. So what happened to our voltage value there? Okay. So remember that your VThevenin, is simply 20 R2 over R1 plus R2. Okay, which is equals to 18 volts. Okay. For the original R2. We have okay, so this is VR2. Okay, the voltage across R2, which is VThevenin, is 20 R2 over R1 plus R2. Now if R2 new is equals to R2 divided by 2, okay, so we are reducing the resistance R2 by half, and we're going to call it R2 new. So what is your new VTH new? When okay, the voltage is still the same, it's 20 volts. And what happens if you put R2 new over R1 plus R2 new? Okay, so how is the VTH new going to change? Is it still 18 volts? Is it going to be lower? Is it going to be higher? So that's what we need to analyze. And in this case, it's actually 20, and R2 new is R2 divided by 2 over R1 plus R2 divided by 2. Okay. So in this case, you're actually going to get 20 R2 divided by 2 R1. So I'm putting it up. So plus R2. Okay. So this is our final equation for the new Thevenin. Okay, our new Thevenin, which is R2 over 2 R1 plus R2. The original is R2 is R1 plus R2, and here the difference is we have 2 R1. Okay, so here you can say that a higher divisor, okay, because now 20 R2 is the same. Okay, 20 R2 is just this value. Okay, on the R1. So if the divisor is higher, then what happened to VTH? So higher divisor, your VTH new is going to decrease. Sorry. Okay. So if you have a higher value on the divisor, sorry, I think okay. Okay. So higher divisor, actually VTH new decrease. Okay, is less than VTH. So it's actually decrease. Okay, so VTH new is actually going to be less than VTH because divisor is higher. Okay, so a higher divisor, and therefore your VTH new is going to be lower. Okay, it's inversely proportional. Okay, so then you can say that VTH new is less than VTH. So what happened is if our VTH new is smaller, therefore our load line is going to shift down. Okay, so initially we have 18 volts VTH. VTH new is probably here. Okay, VTH new is probably around there. So VTH new is less. It's going to be less than 18. Okay, and then what happened to your load line? So this is your original, and this is your new. Okay, so let's say we have something like this. Okay, the characteristic curve is the same. Okay, the characteristic curve is the same. It's not going to be impacted. But now our load line shift down. So what happened when the load line shift down is what happened to our VDSQ and IDQ. Okay, originally it's here. Okay, originally our IDQ VGSQ is there, and now when we shift the load line down, we can see that our VGSQ and IDQ is going to reduce, and therefore our Q point is reduced. Okay, so all your IDQ, VDSQ smaller when R2 reduced by half. Okay, so that's the conclusion we can make. Without going into detail on the calculation, you can make calculation if you want. You can replace the R1 and R2 with some values, and you can prove that actually by reducing R2, we are going to reduce the operating point. Okay, simply because the load line shift. Okay, so that's all for this example, and we'll continue in the next video on the AC analysis for the MOSFET.